Hello everybody. Welcome to our session on renewable heat, environmental impacts and policy evaluation. My name is Tina Fawcett and I'm a researcher at Oxford University, and I'm going to be introducing this session. Before we start, I would just have to tell you we've got two changes to the original schedule on the conference programme. Unfortunately, Denny Gray from CAG Consultants isn't going to be able to join us, so we've got two speakers today. We've got Alex Morgan and also Paul Meyer and Andreas van Giesen are the second lot of speakers. And in fact, we're having to switch the order because unfortunately Paul and Andreas had a sort of time zone confusion, which I'm sure many of you will be sympathetic to. So Alex has very kindly said that he will go first. Before introducing Alex, I'll just give you a little bit of general information about how we're going to run it. Each speaker is going to have 15 minutes instead of 10 because we've got our two speakers, so we've got a chance to hear about their work in more detail, which is great, and then we'll run the Q&A as normal. When you have questions, please type them in the live Q&A chat box at any time, and remember to put the speaker's name at the start of your question so I know who the question is for. There's a discussion forum as well. That's for more general discussions with fellow delegates, but that's not for putting the questions in the Q&A. So just use that for more general chit chat if you wish. We're not using the raise hand feature, so please don't use that. If you need technical support, there's a little red live technical support icon in the top right of your portal, so please use that if you need to. So that's the general housekeeping. Right, I would now like to introduce Alex Morgan. Alex studied a double degree in chemistry and chemical engineering at Sydney University, and then he studied for his master's degree in sustainable development at Leipzig and Utrecht universities. Since completing his master's degree, Alex has been employed to project manage the installation of a school biomass district heating system, a project which will receive support under the domestic renewable heat incentive scheme. So it follows actually practical experience following on from the research evidence that he's going to present to us. So I think that will be really interesting. So I now welcome Alex to begin his presentation.
Great, thank you very much for the introduction, Tina. I'll be presenting some of the key results from my master's thesis paper, and this looked at evaluating instruments stimulating sustainability transitions, and specifically looked at promoting biomass boilers for renewable heat in Germany and the UK. So I'll start first by describing the research question, and then move on to the methodology that I adopted, followed by some key results from the study, which is where we'll spend, I guess, most of the presentation on, and then finish with a conclusion. So, as you would all be aware, biomass boilers are one renewable energy technology which can contribute to the decarbonisation of heat, and consequently, countries have adopted policies to promote their uptake. In my study, I looked at comparing the key economic instruments adopted to achieve this by Germany and the UK. So in Germany, the Marktanreiz program, or Market Incentive Program, has been in place since 1999, and it operates by providing an upfront investment subsidy, which will reduce the capital cost for eligible biomass boilers. In contrast, the Domestic Renewable Heat Incentive, or domestic RHI, was launched much more recently in April 2014, and it operates by providing a tariff payable on the amount of heat generated by eligible installations for 7 years after they've been installed. So the specific research question that I asked was, how do the key economic instruments promoting the uptake of small-scale biomass boilers in existing residential dwellings compare between Germany and the UK? So I approached this research question by evaluating each policy instrument performance at two different levels. The first level looked at the assumptions underpinning how each policy is meant to operate to meet its objective, namely its program theory. For example, for people to apply for the scheme, they must first, of course, be aware of it. and each policy therefore must have a strategy in place to ensure that the target population is aware of the scheme. I also evaluated the instruments using abstract design features, and these are recognised in the literature as desirable characteristics for instruments promoting sustainability transformations. To support the evaluation, I undertook a review of academic and grey literature and also conducted semi-structured expert interviews with experts from business, the government and industry. Business, government and academia. Talk about findings briefly. So the first relates to the differences in stringency levels between the market incentive program and the domestic RHI. The stringency is defined here as the ambition level of an instrument with respect to its innovative push. The greater the stringency, the greater the incentive to change. And as you'll be able to see in this table here, the market incentive program is a more stringent instrument. If you look at the particulate emission limits, all the emission limits across particulates, carbon monoxide, nitrous oxides, they are more stringent than that of the domestic RHI. And in addition, the biomass boilers to be eligible must have a much higher minimum efficiency. So this then, of course, this higher stringency ensures that, or pushes manufacturers to develop boilers which meet these standards. And in addition, the market incentive program did also place an explicit emphasis on promoting innovation. So the scheme has provided higher subsidies for boilers with condensation technology and also secondary particulate separation, which reduces emission levels even further. For the domestic RHI, a lack of stringency was identified or stated as an issue for the scheme by several interviewees. And of course, with these less stringent emission limits, this results in higher air pollution. And this may have been a possible consequence for the proposed ban of biomass boilers from gas-connected urban areas in 2018 by the Department for Business, Energy and Industrial Strategy, or BEIS. Moving on to the second key result. So this was looking at the differences in predictability across the two schemes. So predictability is defined here as the degree of certainty associated with an instrument and its future development for impacted stakeholders. And an ongoing challenge with policy instruments promoting sustainability transformations is that it's trying to maintain the balance between having a predictable instrument, but also to have the flexibility to cater for changes in a dynamic market. Firstly, looking at the United Kingdom, on this graph here, I have time down the bottom on the x-axis. The blue columns are the tariff rates payable in pence per kilowatt hour, and the orange line is the quarterly number of accredited installations under the domestic RHI. So going through time, you can see that at the beginning of this scheme, there was a rapid uptake in the number of biomass system accreditations. But inbuilt into the design of the domestic RHI were automatic digressions or reductions in the tariff rate payable if the uptake for a certain technology was higher than sort of preset levels. And this occurred for biomass boilers under the domestic RHI. And from 2015, you can see there were sort of sharp drops in the tariff rates payable for biomass boilers. And this consequently led to a decrease in the uptake of, or a decrease in the number of applicants for the domestic RHI for biomass boilers. And this, and obviously the decrease in the tariff rate payable significantly reduced the competitiveness of biomass boilers. And it was pointed out by several of interviewees that, they believed that this reduction in the tariffs payable was too aggressive and, severely impacted the market To sort of lay out some of the key reasons why this possibly occurred, and what are the reasons for this trend. Firstly, it seems there was potentially an error in the setting of the original tariff level. It was set too high. And in addition, the instrument design required time-consuming parliamentary approval for scheme modifications. So these automatic reductions in the tariff rates payable were ongoing, but there was no way to sort of reverse or to alter the design at that time. And even though at the end of 2016, the instrument was changed so that directions could not occur if the uptake of a technology had dropped substantially. This, of course, was too late for biomass boilers who already had very low uptake figures at this time. Moving on now to Germany. So Germany also struggled to maintain predictability. I have a similar graph here to the previous slide. So we have time indicated on the x-axis. The columns here indicate the upfront subsidy payable for a biomass boiler in 2017 euros. And in the orange indicates the uptake of biomass boilers under the market incentive program. So the challenges faced in Germany were slightly different. There were actually about 17 changes to the funding amounts or eligible technologies between 2001 and 2012. And if, for instance, at one time, log boilers were excluded from the scheme, and then they were later reinstated. And in addition, there were some funding shortages across the duration of the scheme. For instance, in 2006, applications were rejected due to a higher than expected uptake, which exhausted the budget. And consequently, at this time, due to the high uptake, the subsidy rate payable was also substantially reduced. You can see the reduction in subsidy rate payable there in 2006. In addition, in 2010, largely as an outcome of the global financial crisis, the scheme was frozen for about 2 months. And even though the freeze was only for a short duration, stakeholders did claim that it impacted the market and drove a decrease in the faith in the reliability of the government. And you can see it was a sharp drop-off in 2010 in terms of uptake. And these feelings from industry stakeholders may have had some contribution to the time it took for the uptake to increase in the subsequent years. So yeah, to sum up the comments on predictability, both the market incentive program in Germany and the domestic RHI in the UK did struggle to maintain predictability over the duration of their schemes. Okay, so moving on to the final key finding from my study. This relates to challenges for the uptake of biomass boilers in the UK. So the level of support, the level of financial support in the UK for biomass boilers is significantly higher than that of Germany. So for instance, a 25 kilowatt reference pellet boiler generating 20,000 kilowatt hours annually would receive 3 times as much support under the domestic RHI compared to the MAP. However, the market incentive program does subsidize about 10 times as many boilers every year. So why is this? Well, my research, of course, not providing all the answers, but had a few possible explanations which could have contributed to this question. And first one was a lack of awareness. So between 2015 and 2017, only 18% of homes off the gas grid, and this is the target market for biomass boilers. The target market is to sort of replace oil or other boilers that aren't on the gas grid. Only 18% of these homes were aware of the domestic RHI. Secondly, the challenge of having an upfront cost barrier. So upfront cost was recognised as a key concern for 62% of domestic RHI applicants. And of course, biomass boilers can be quite expensive. I think for a 25 kilowatt unit, it's something around £10,000. And not having sort of a subsidised loan scheme or a way for people to borrow money to overcome this upfront cost could certainly have meant that people wanting to install biomass boilers weren't able to because of this upfront cost barrier. And finally, another explanation could be competition within the scheme. So in the domestic RHI, this comparative levels of support provided to ground source and air source heat pumps is much higher than that of biomass boilers. And this is when you compare it to the German market incentive program. So you actually, relatively, you will receive a lot more funding for ground source and air source heat pumps in the UK than you would in Germany. And this may be driving domestic, people wanting to install these systems to preferentially choose air source heat pumps or ground source heat pumps rather than going for biomass boilers because they're preferable from an economic point of view. Okay, and now we're on to the conclusion. So just to restate the research question. So this was, how do the key economic instruments promoting the uptake of small-scale biomass boilers in existing residential dwellings compare between Germany and the UK? And this was achieved by evaluating both the market incentive program and the domestic RHI with respect to their program theory and abstract design features. The key results that I shared with you today were that the Germany market incentive program has a higher stringency and also therefore a greater innovative push than the domestic RHI. Secondly, that there was a lack of predictability in both countries, and this was observed to impact the uptake of biomass boilers. And finally, that there are challenges for biomass boiler uptake in the UK. Even though the level of support is significantly higher, uptake is quite low. And yeah, that concludes my presentation. Thank you.
Brilliant. That was great. Thanks very much, Alex. Just to encourage everybody in the audience to start putting your questions in the Q&A so that we can do the questions all together once we've heard from our second presenter. So I'm delighted to say that Paul Meyer and Andreas van Giesen have managed to overcome the problems of time and space and are going to be with us to give their presentation. Paul is a senior research advisor to Boundless Impact Research and Analytics. He has over 20 years of experience in energy sector analysis, air quality research, and decision support technology. He is also an adjunct professor at the Center for Sustainability and Global Environment at the University of Wisconsin-Madison. And he is the founder of Juicebox software, which was used for the electricity sector modelling as part of the analysis presented today. His co-presenter, Andreas, is a research analyst at Boundless Impact Research and Analytics. He works particularly on climate in their climate impact assessment team and specialises in life cycle assessments of energy storage, waste to value and biofuels. He graduated from Delft University of Technology in the Netherlands in 2018 with a master's degree in management of technology and focusing on infrastructure and environmental governance. So we're going to be in very safe hands to hear this presentation. So please start.
All right, thank you for that introduction. Good afternoon, everyone. My name is Andreas. I will be presenting today along with our senior research advisor, Dr. Paul Meyer, on the life cycle assessment of US biomass supplied to the UK and its role for meeting UK emission objectives. Just a quick introduction. Boundless conducts and evaluates impact assessments based on the life cycle analysis approach of clean tech companies, typically on behalf of startups and investors active in the impact investment space. We do this so that these companies can show and highlight their environmental performance using a science-based approach. And every now and then, we also write white papers and peer-reviewed articles on critical clean tech subjects. Today, we are presenting results of a study funded by Enviva, the world's largest supply of wood biomass pellets. And to remain independent, we always work with independent experts to support our work and write peer-reviewed papers, ensuring a neutral study from our side. For this, we would like to acknowledge Corbett Eckert of Momentum, based in the US, and Charles Levesque of Innovative Natural Resource Solutions, also based in the US, for undertaking the independent peer review. Let's see, right. So our research into wood pellet, biofuel, and electricity generation focuses on the requirements to deem wood harvesting practices sustainable, as well as to quantify the carbon intensity and other relevant environmental factors of wood pellet electricity and alternative generation technologies. Lastly, we evaluated the market impact of wood pellet electricity when it's deployed at power plants in the UK, Germany, and Japan. Let's go to the next slide. So one of the most important things is to see what are the conditions for sustainable working forests and what are the regulations and guidelines. Obviously, with any type of biofuel and with biomass, it's important that the source is sustainable, as it has a dramatic effect on the greenhouse gas impacts. Under the European Renewable Energy Directive regulations, there is a focus on land use change. Wood coming from forest that is not being regenerated cannot qualify as being sustainable and cannot qualify as being biomass. Then it's important to look where is the coming from. Typically for wood pellets, it's low-grade trees, it's trimmings, it's basically waste from the timber industry. And then on top of that, there's third-party certification by organizations such as the Sustainable Forestry Initiative, the Forest Stewardship Council, and the American Tree Farm System. So these are all sort of guidelines and regulations in place to make sure that the source, being the biomass in the US, is sustainable and actually meets all the regulations that are there. And then another point is that to be able to say something is long-term sustainable, you need to look at the long-term assessment of a forest managed. And what's interesting is that a lot of these forests that are currently being used as biomass, they have been working forests since the 1920s. They're not wild forests that are being cut down and regenerated. They are already working forests. And over time, it's important to look at the forest area and the volume of timber over time. A very important note to make is that the carbon that is released as CO2 during biofuel combustion, it's continuously balanced by CO2 uptake from forest growth, and therefore it's deemed carbon neutral. My colleague Paul will discuss this a little bit more in detail later on, as it's a very important assumption and topic within biomass. So in this case, the case study we did for the UK using wood pellets from the southeastern US, we looked at harvesting and transportation forest products to the pellet production plants. We looked at raw material handling, as well as emissions during storage, obviously wood pellet production, and then transportation all the way to the UK to be able to combust it in a power plant, as well as the energy conversion, which again holds the carbon neutral assumption that Paul will discuss later on. So using our analysis based on life cycle analysis, we compared how wood pellets without combined heat and power and with heat and power scores on the greenhouse gas intensity factor relative to coal, natural gas, wind, and solar. And what we see is that relative to coal, almost 86% greenhouse gas reduction can be achieved relative to coal when you're burning wood pellets without CHP. It's a little bit higher for solar and wind, 92 and 97%. However, with wood pellets biomass, there is the advantage of having a continuous base load. Now, comparing this to natural gas as well, we can see a 68% reduction in greenhouse gas intensity. Again, 82 and 94% for solar and wind relative to natural gas. But the most important outtake from here is that with wood pellet biomass, you have a continuous load. And a side note is that we do not advocate one technology over the other. Each of these should obviously be researched objectively without appreciation for the specific circumstances. And with that, I am going to hand it over to my colleague, Paul.
Thanks, Andreas. Do you want to advance one slide for me? Thank you. So as Andreas said, in conducting this life cycle assessment, one of the key assumptions is how to account for the carbon in the biofuel itself. There's lots of literature around biofuel life cycle assessment in terms of the energy and emissions from harvesting and processing. But in recent years, the carbon cycle has become increasingly controversial with some popular press articles stating that biofuel may not be carbon neutral and that there might be long multi-decade payback time for biofuel to recover a carbon debt. And so we looked into this issue, and a couple of different things that we did is number one, we sort of looked around the circumstances around the particular feedstock that are used for this wood pellet fuel. And as Andreas said, this raw material is derived from working forests. So these are forests that have been in continuous harvest and regrowth for a matter of decades, if not approaching a century. The region of this resource is the Southeast United States, and the overall region has experienced net increases. And so that is at a macro level a good indicator that the net economy around the biofuel industry in this region is not a carbon source. In addition, as Andreas said, the raw materials are a secondary product, so there's primary timber harvest that's occurring, and the source material for the wood pallet is the mill residues and the byproducts of the forest forest harvest. And then finally, in accordance with EU regulations, none of the biomass is derived from the conversion of forest land to non-forest uses. So that tells us a little bit about the raw material. The other issue gets into a life cycle assessment accounting issue. So the idea that maybe biofuels accrues a carbon debt is really a function of the rules that you apply when you account for using a biofuel. And what we did was take a relatively simple model of carbon as the forest grows and is used in the system that we evaluated. And that's shown by the two graphics on the right. At the top, we show what I would consider like a conventional view of biofuel, where you are crediting the carbon uptake during forest growth. To me, this is sort of a common sense approach where literally the atmospheric carbon is absorbed into the tree as part of its growth. And what you see then over a period of 30 years, as each stand of trees that is going to be part of this system plants and grows, that there's an increase in a carbon sink. And then about halfway down that chart, you see there's an orange bar that sticks up into the positive. And that's the first harvest where there's energy and emissions associated with harvesting and processing the fuel. And then the combustion occurs. And the net effect of both of those things, the forest growth and the consumption of the fuel, is shown by those green circles. So there's a carbon sink followed by use of the material. And you see that there is a net positive, but it's very low. And in fact, it's right in accordance with our studies how that math works out. Now, if you use a different type of accounting where you say, well, we're not going to provide any credit to this fuel until the point of combustion, which some folks have proposed, then you see what's in the lower graph. So the forest uptake that occurs, the carbon uptake that occurs in the real world is ignored. And then you have a positive impact when you use the fuel. And then over time, as you replant, you would reduce that. The point I want to make is that if you look at either system and you treat them identically over a long period of time, what you see is that the steady state conditions end up the same. So when you look at the difference between the green dashes, the green circles in the top graph and the brown circles in the bottom graph, they end up at the same place, and it's accounting practice that makes the difference. Next slide, please, Andreas. So we used the life cycle assessment results for this fuel as Andreas presented them. Again, we assume that the fuel is carbon neutral, and then we deployed this fuel in a simulation of some national power sectors. On the left, I'm showing a graphic of the UK. On the right, a graphic of Japan. And what we wanted to examine was what is the contribution that this fuel might make in terms of national emission goals. In the UK, we looked at a policy objective which was to achieve a 59% emission savings by 2030. And the first technology that people think of in expanding renewables is solar and wind. And what we wanted to test was if we expand both solar, wind, and biofuel at basically the same percentage versus ignoring biofuel, what is the difference? On right, for Japan, we have a little bit different scenario. Japan has had many nuclear reactors closed, and several of those are at higher risk for not reopening. So what we wanted to examine is, could biofuels, basically converting coal plants to biofuel, provide a hedge for Japan? Should nuclear plants not reopen, could they still maintain their international commitments? Next slide, please, Andreas. So here are the results that we see for the examination of the UK. So in the dark green line, what you see is the long-term trajectory, the emissions trajectory that's achieved when wind, solar, and biomass are all expanded, and it indeed meets that target of 59%. The difference is if you ignore biomass and you expand only wind and solar, the result is that dashed yellow line. So importantly, as Andreas said, we're technology neutral, but if you add additional low carbon resources, you're always going to end up then with a lower total carbon footprint in the power sector. And the dashed green line I show there also includes some additional retirement of coal. Next slide, please, Andreas. Here we look at some CO2 trajectories for Japan. And in the dark blue line, we see the trajectory where the nuclear units successfully restart, and they provide 22% of the renewable generation mix. In the dashed blue line, we see the trajectory if some of these high-risk nuclear units are not able to start, and you see that there's a significantly higher CO2 output by 2030. So then what we did is we added in this wood pellet biofuel, substituting for coal until we maintained the first trajectory. And what we found is that Japan would have to increase its biofuel contribution from about 4% to about 10% to provide an effective hedge against nuclear units not restarting. Next slide, please, Andreas. So here in summary, one of the important aspects about this resource is that it can provide basically baseload and intermediate power for periods when other renewables are not available. And that's a really important aspect for grid operators who are trying to provide stable electricity. What you see at the right is many studies, this is from published by Drax, that looks at the storage requirements as the penetration of renewables approaches 100%. So with only variable renewable energy, there's very high storage requirements for a grid to operate with resilience. So now, while natural gas has great properties for backing up renewable electricity, we also know that there's a much higher greenhouse gas footprint for natural gas. So we really see this wood pellet biomass generation as a relatively low cost way by converting coal plants at a relatively low capital cost to use this fuel. It can provide grid operators with a reliable fuel that can really match well with the intermittent renewables and provide a low overall carbon footprint. So with that, Andreas and I would like to thank you and conclude. Thank you very much.
Brilliant. Thank you very much, Andreas and Paul. That was great. We've now got opportunity to have questions to all three speakers. We've got a set of questions already in the Q&A, so I am going to begin with those, and we'll have a couple of questions to Alex first, and then we'll move on to Paul and Andreas and other questions as they come up. I've got some questions of my own, but it's looking like I may not get a chance to ask them because there's quite a lot of interest from the audience, which is fantastic. So let's start with questions from Simon Stromberg. These are for Alex. And he's asking two questions. And I think you can probably take them both. The first one was whether there's a big difference in the way that information is disseminated in the UK and Germany, and whether there's any learnings for policymakers. And then the second question was about take up of heat pumps in the UK. What does that look like?
Okay, yeah, thank you for the questions. Preface my comments by saying I'm not an expert in these matters, but through my studies I did come across some information that could be useful. The first point would be that obviously this scheme's been in place for much longer in Germany than the UK, so I guess there's been more time for people in the public to become aware of the scheme, and that would increase knowledge and awareness. Additionally, there's a bit of more of a big emphasis on subsidized consultation support in Germany. So I think it just can't remember what it's called exactly, but it's the independent at the Federal Association of Consumer Affairs, and that's been in place for many years now, and that offers heavily subsidized consultation support. Up sort of 80 to 95% costs are covered by the government, and this can be as simple as like little checks on your house to understand energy efficiency improvements and the costs associated with doing that, to sort of more in-depth evaluations and plans to reduce emissions in a staged approach in the future. So they're sort of a couple of reasons why there could be potentially better awareness in Germany. I don't know specifically about sort of direct advertising, so I can't comment on that, but hopefully that gives you a few points to answer that question. And then on the second question about the uptake of heat pumps, comparing that between the UK and Germany, I had a quick check of that, and the uptake of heat pumps is higher in Germany than the UK, but not significantly so. So just pull that out. So for instance, in 2017 and 2018, there are about 18,000 heat pumps supported in Germany and approximately about 7,000 heat pumps installed in the UK. So it's definitely not as drastic a difference as the biomass systems, where there was a 10 times different, but there is still more heat pumps being supported in Germany than the UK. A couple of qualifiers to those numbers is that the market incentive program supports existing and new buildings. So that means there's slightly more buildings that are eligible for these systems. And maybe one of the interesting points is that it's actually only quite recently that Germany started to support air source heat pumps in any fashion. So it's only, I think, since sort of 2016 that they've started to provide more subsidy support for air source heat pumps, whereas previously they didn't. I don't know how much support, but it was much less or not there at all prior to that date.
Okay, brilliant. Thank you. I'll just ask you a quick question before we move on to one of the questions for Paul and Andreas, which is, do you know where the biomass came from for the systems in Germany and the UK? Just thinking about their study and biomass around the world.
I think I believe that it's almost all domestically sourced. So for domestic buildings, it's almost all sourced locally within the UK. I'm not 100% sure of that, but that's my understanding. So for instance, in my industry work now, it's a 1.6 megawatt biomass system being installed, and we're sourcing that locally from estates and other companies within a 40-mile radius. So the intention is to support this from relatively close location, and that we're only considering domestic sources of wood chip for this project.
Yeah, brilliant. Thank you. That's right, and I think that moves quite nicely to some of the questions for Paul and Andreas, because obviously the studies you're looking at are on a much, on a huge scale, using biomass in power stations, and that's quite a different set of considerations. And we've had quite a lot of detailed questions for you coming through on the Q&A, as you've probably seen, about the details of carbon accounting in various different ways. I think if we start with the question by Olivia, and so I'll just read it out. She says, I appreciate that current biomass supply from the US can be considered carbon neutral, considering that current suppliers rely on these lands that have been in use since the 1920s, as you explained. But if we require an expansion in supply to meet the UK's demand for biomass, would this generate an increased need for other land to be used for biomass growth? And could this additional demand be met in a carbon neutral manner? So what's the risks of growth of this market?
I will take this one. So this is definitely a valid question, and obviously to say, if there's so much demand that century-old forests need to be cut down to be regenerated into 30-year cycle growing forests, working forests, that might affect the greenhouse gas impact and the carbon neutrality assumption. The location and the case study we looked at is for the southeastern US, where almost all of the forests currently are working forests and are already using byproducts of timber industry and other industries. So there's definitely a lot more room there for demands. On top of that, there is a positive relationship between the demand for biomass and the forest volume. It's important to talk about volume instead of just area in general, because area in general doesn't say anything about the quantity of woody bioproducts.
Do you want to add anything, Paul?
Yeah, I would concur with Andreas, is that the overall trajectory has been with increased demand, that in the area of our study, the southeastern US, that the forest has expanded. So it is, it's an important question. And, our stance is that, every stand of biomass used for energy purposes, should be evaluated for its case-specific properties. Where did it come from? Is it a part of a sustainable supply chain? So we recognize the importance of the question, and then there's what we're getting at is how much total out there is there, right? We know we have a finite amount of land available, and we have huge energy needs. So at some point, yes, I mean, if your question is, is it going to, provide all of the baseload power? No, but I think that, we have relatively modest increases, and I think the levels of increase we're looking at, could be important at a national scale for mitigating the challenges of intermittent renewables.
Yes, and I think you made it very clear in your paper and your presentation that that's right, that this case-by-case approach is a vital part of having a valid set of answers from the methodology that you're applying. So to go to another question, if we look at a question from Camilla, and so she's got a couple of questions. Let's go for the first one first. It says, do you have any thoughts on accounting for the carbon impacts of taking that wood out of other supply streams alongside the land use change impacts previously mentioned? So I guess that means, what would that wood waste have been used for otherwise? I think that is the meaning of the question.
Yeah, good question. And, I'll try this first, and Andrea, you can help me improve. So, one of the important things that could happen to that wood is, sometimes that wood could be left behind in the forest. And so it has an ecological impact by being left there, right? And so there are researchers who do study the difference between removing additional amounts of forest harvest versus leaving them in place to decompose. So that is another important aspect. How does the long-term soil accrual of carbon change when that's removed? And so again, we recognize these as important questions, and it's part of what, again, has to be part of that case-by-case analysis. Again, and just to reemphasize, what the resource that we're looking at is always a secondary product. That's the supply chain that Enviva promises and that we evaluated. So there is a primary timber harvest that is assumed as part of our study. Andreas, can you add anything to that?
No, I'm not sure at the moment. Thanks, Paul.
Okay, great. Well, I think that was a very comprehensive answer. I have got some more questions for you two, but actually I'm going to take another question for Alex at the moment. So this is the question from Robin, and it says, in the Netherlands, the main investment subsidy for heating installations for dwellings was removed for biomass boilers, amongst other things due to concerns about fine particulate matter emissions and the health impacts. And how is this taken into consideration in stimulating biomass further in the countries that you looked at?
Yeah, that's a good question. I don't know if I can completely answer it, but I do know that there is recent development looking at ultra-low emission gasification biomass systems currently in development. So these don't need to have a secondary particulate separation, and they have extremely low emissions. And obviously that is desirable from an air pollution point of view. As I showed in the presentation, the particulate emission limit in Germany was 20 milligrams per meter cubed. And I don't know the answer as to what sort of impact that has on health. Obviously that limit was set for a reason. But yeah, I would suggest that that's an important question to be answered, because yeah, I can't answer and say whether that is okay for everyone in terms of health, or if it needs to be more stringent. So that's obviously seems to be the important question. And then obviously the density of these biomass boilers and how they sort of contribute to overall air pollution.
Great, thank you. Thanks very much, Alex. Just to follow on from that to Paul and Andreas, do you look at all at local air quality impacts of combustion of the biofuels in your studies?
We did not look at that as part of this study. I think it's an important concern. In our case, our assumption is that we are substituting the wood pellet biofuel for coal. So what you have to examine is the net change. So in terms of what's going to impact human health from coal combustion, there's emission of nitrogen oxide, sulfur dioxide, which then have conversion to fine particulate along with direct emission of fine particulate. When you substitute biomass, you're still going to have nitrogen oxide and fine particulate. I would anticipate less sulfur dioxide. So then in any like power plant situation, it's very complex, like how the combustion process in combination with the pollution controls at each individual facility. And those pollution controls can be very capital intensive. So I hate to sort of say this to every answer, but it ends up being like very site specific at each boiler. And it will be certainly like something that will be considered, I think, with each individual conversion.
Okay, I mean that's great. Thank you. So we've got a couple of more technical questions again for you. So let's go to the one from Simon, which is, so he's asking a question about your calculations, as you can see, and I'll read it out. It says, were you talking about operational greenhouse gases or full cycle greenhouse gas emissions, including construction, decommissioning, transport, and land use change? And then he refers to a recent paper in Nature by Pale et al. I don't know if you've seen that, and suggests an overall higher carbon budget for biomass. And then he finishes by saying, I'm struggling to understand how you match solar for greenhouse gas emissions. So it's partly about the boundaries, I guess, that you've used in your study. So would you like to comment on that?
Yeah, I think in terms of scope, it is full fuel cycle. The only thing you mentioned there that we did not include is the embedded, so like facility capital. So in our case, we're assuming a conversion of an existing coal facility. So, might there be some new equipment? Yes, that was probably the one thing we neglected, I guess, in all of my life cycle work. Like, when you amortize the, equipment over 30 years, it tends to be very small. And in this case, there's not a lot of new capital anyway. Otherwise, we do think we are relatively comprehensive in terms of what's typically reported in the literature. Because we're using resources from working forests, there is no land use change associated in our study. And, like you said, you've pointed out a study that shows, a higher impact. I don't doubt that that's possible under certain circumstances. We feel pretty confident that, in the work that we did, and that it aligns with similar work for similar resources. In terms of how that compares to solar, we use an array, and Andreas can maybe step in here, but we look at lots of published literature for solar and wind. And one of the things I think that works slightly against solar is that, if you build a PV facility, and you deploy that in the UK, you've got a relatively low capacity factor. So how much energy you get out. So, the solar energy is slightly penalized by not being a large, annual producer of electricity. But overall, I mean, as Andreas showed in the slide where you compare these technologies, they are all, 86 to 97% lower than coal. So from my personal perspective, that's the challenge. It's displacing the coal and the natural gas with these other lower carbon resources, and doing it in a way that's economic and provides a reliable grid. So I do not like pitting these low carbon technologies against each other. I think we need all of them, and in fact more of each of them.
Yeah, great. Did you want to add something, Andreas, or?
No, I think Paul covered everything.
Okay.
Just to say, we, with the solar and wind we combine data from small and large solar and wind farms to make sort of an average for the data we used.
Yeah, and I would just encourage everybody to read the paper, actually, because that's very, as you would expect, it's very detailed, and it explains in great detail, what methodologies have been used, where the data's come from, how it's been checked by independent experts, and so on. So if you're interested in the really fine detail of how all these calculations have been done, and obviously that's very important, then do read the paper, because that will give you much more information than it's possible to get across in a sort of short presentation. I've got a question for Alex, which I was just wondering what your now that you're working as a sort of somebody who's using RHI, using a sort of renewable heat incentive scheme to put some biomass scheme into a school, have you, by being part of the scheme, have you got any additional insights that didn't come out in your study, or is there a contrast in your experience?
I guess a little bit. Well, it's not so much a contrast, but just gaining sort of a greater appreciation of what the incentives are at the ground level. So, we're dealing with this biomass installer contractor, and when you look at it from a research policy point of view, you're thinking, what's the long-term cost-effective way to achieve these emission reductions? Whereas on the ground, it's about, can I get this in as cheaply as possible? And, for instance, we are putting in 2 biomass boilers, which are 800 kilowatts each. And we selected boilers below 1 megawatt because that means that they don't fall into the requirement of having an environmental permit, which limits emission levels. So basically, by going with 2 smaller units, you avoid having to adhere to these emission limits. And if we had to adhere to those emission limits, we would have had to have put on secondary particulate separation technology, which is quite expensive, costing about £60,000 per unit, would have made the project more uneconomical. So I guess it's just sort of gaining an appreciation of how the policies and the objectives of the policies and regulations, I guess, attempt to, how the installers try to work around those, and yes, you avoid them to serve their own benefit, basically.
Yeah, interesting. Yes, and well, there's this tension, it seems, between, well, possible tension between air quality and reducing carbon emissions, although it seems in Germany, by setting stricter standards, that hasn't been such an issue, perhaps.
Yeah, and I would also add that there are a hell of a lot more oil boilers in Germany than there are in the UK. And that's sort of the main target market for biomass boilers. So that, and there's obviously more area in Germany than the UK between farms and things like that. So you can get around some of those air quality concerns more than you can in the UK.
Brilliant. Well, we've still got some outstanding questions, but we haven't really got time to deal with them all. I mean, you can see them, and if you want to respond to the questioners in text, you speak as you can. I'd just like you to each give me sort of less than a minute on what you see as the future for the thing that you've been studying, whether it's large-scale use of biomass or smaller scale. So, Grace and Paul, if you'd like to go first.
Sure, I'll go first. So I'm actually going to answer Camila's question for my 1 minute.
Okay.
Yeah, we looked at solar and wind because they're one of the most popular technologies, renewables, to look at in long-term expansion. We do see biomass as a transition. I do see biomass as a transition technology, while solar and wind and other renewable generation technologies can further develop to be able to go to a grid where we get like 50% or a certain amount of renewables as quickly as possible. Biomass plays an important role in supporting that until other technologies can be further developed and can meet that demand. And that's also where we sort of go back to the previous question that was asked about, like, okay, the demand for wood pellets long term, if you move an entire grid on wood pellet biomass energy. So it's I really see it as a transition until other technologies can be further developed. Thank you.
Brilliant. That's great. And Alex, a few words from you about what you see the future of smaller scale commercial and household biomass.
Yeah, I think my research showed that it's, obviously the policy mix is really important here. It seems that in the UK, at least, there's a lack of awareness about the scheme, and there's also not other instruments complementing the subsidy schemes to overcome upfront cost barriers. So, and obviously, the uptake rates need to be higher if we're going to get to net zero by 2050. So, just emphasising the importance of more cost-effective complementary policies that can sort of help boost that uptake without costing much more.
Brilliant. Well, I mean, I would just like to thank the presenters for this session very much. You all did really well. I know it was not at the time you quite expected for Paul and Andreas, but you came here, you got here, which is brilliant. I'd like to thank all the audience for the fantastic range of questions. I'm sorry we didn't get through all of them, but I think we got through most of them. Just to remind you that after this, we've got the North-South networking function that you can join if you wish. and there's other more general places to meet people in the meeting hub. So we hope you have enjoyed the presentations, and look forward to seeing you online again tomorrow morning at 10 a.m. Central European Time, 9 a.m. UK time. Thank you very much.